In today's topic, we're talking about switched capacitors, which is a sort of nice way in integrated analog circuit design to avoid the use of resistors. Resistors are typically noisy and they are a bit bulky, and they're also associated with a pretty big parasitics. We might want to implement the resistor like, an element like this. But if you look at the physical implementation of this one, it's probably going to be some sort of long strip of some material on your chip, a certain number of micrometers, and that particular strip is also going to be associated with parasitic capacitors, etc. So they are typically more troublesome. And one could argue also that a resistor is an element which consumes power, so it's going to become heat. Now, the argument against switch capacitor is not that crystal clear, but at least the resistor then is sort of considered to be an evil element which we want to get rid of. And we also do not want to use inductors. They are also big and bulky. If you look at an integrated inductor on a piece of silicon, it will typically be a large component in like a coil like this, and also this one will be associated with parasitic resistors in the wires that will then influence the parasitics, and that will reduce the Q factor of the inductor. So we will typically have bad Q factors. So the idea here instead is to find an element which can mimic these components. Today we're going to look at the switched capacitor, which then can mimic the resistance or the resistor in the component. So let's look a little bit on how we can do that and start with the basics. So we think of a resistor or a capacitor like this. So we're going to mimic a resistor in the end, but let's start look at the capacitor in this way. C, where I have an input Vin and an output V2 or V out. Let's call them V1, sorry, and V2 instead. And then I have a switch here. And the switch we can typically implement with a MOS transistor. So quite easy to implement a switch with an NMOS connector like this, and I just have a clock signal on the gate, which then turns on or off this device. And then I can combine a set of transistors to get the switch, a three-way switch or a four-way switch or anything I like. So now the trick is to consider charge on the capacitor. So I would, for example, be able to notify or note charge like this, a set of holes and electrons on the capacitive plate. And it also depends on the voltage direction, if it's positive or negative. But at least I'm able to then specify that the charge on the cap is typically equal to C times V. So if I have a certain voltage and I have a certain capacitance, then I also have a certain charge on the device. So what could we do here? Well, first we have to think about what this switch is doing. It's actually a sort of sampling happening here. So I have, if I would measure V2 here, I'm not sure what's connected here on the other side, but if I would look at the wire here during this phase, when the switch is connected like this, there won't be any change of voltage in V2. And then in the other phase, when I go back, so let's just draw this case like this. And then I have a V2 here, and I have a V1 here. And we should say also that V1 is our input, so I typically have some voltage driving this side of the capacitor, the switch capacitor. So I have a case where I charge the capacitor, and then I disconnect to this case, and then dependent on what's connected to V2 here, I'm able to move that charge from the plate out to V2. So, but I do have a sampled environment. So I have one phase when it's connected like this, and I have one phase when it's connected like that. So I have to consider my circuit in two different time points in order to understand it. All right, so what's happening is that I'm going to charge my capacitor during this phase with new fresh charge from the voltage source. If that voltage source has a negative potential, it would steal charge. So for us, it's just a sign, but it's either going to give charge or remove charge from the capacitor. And once we get to this phase, it's going to transport charge to the output or move or stay as it is if we don't have anything connected to V2. So conceptually, with switch capacitors, I do have simple ways of implementing the switch with a MOS transistor. I can take some metal plate, I just take some metal flakes and put them close to each other, and then I have a capacitor. And then I'm able to switch back and forth in order to move up charge and remove charge. And if you think about this, this is actually acting like a resistor. I have a net flow of current to this device, and I have a net output flow of current from the device. That's exactly what the resistor does. You have a voltage applied to it, and it steals charge as in if it would be a current. So let's look at the maths behind this then. Okay, so we have to introduce some methods. So first we agreed that we had two different phases, and then first phase. So during the first phase, we note the charge on the capacitor. We assume we have numbered the capacitor because we could have plenty. So the charge on the capacitor at that phase, which is a multiple of the clock sampling period. So T is the sample period. That's going to be equal to C1 then times V1 of NT. Okay, so one could think of this, say we have a sampled or at least a time domain like this, and then we have a signal varying. Okay, and then I have 1T, 2T, 3T, coffee and tea like this. And then this system is going to capture the voltage right at the end of that period. So at these points. Why at the end? Well, it doesn't really matter what's happening here. We assume a very low resistance in the switch here. And then this charge transportation is instantaneous. If we have resistance here, it will be a certain time delay. But that's not the case here. So it's going to sample the signal at the output here simply and store the charge. And V2, we don't know much about at the moment, the way we have connected it. So for V2, we simply say that it's going to be equal to V2 of NT minus tau. And tau is just a way of minimizing the notation here. So tau is simply going to be equal to T half. So the other half phase of the switching. Also here, it might not be that we have 50% duty cycle. It could be that we charge 90% of the time, and then we move to the output 10% of the time. So that's why we use a tau, just in order to be flexible here. But typically half, one would say. And in this particular case, we're going to use T half. So we'll see that. Sometimes one also writes, like Q1 of T or Q1 of N, or sometimes we indicate the phases and just type Q1 of phi 1 or Q1 of phi 2 to indicate the other phase. So we have some different ways of handling this. Okay, so then that's the charge of the capacitor during that phase. So this is when the switch is connected like this. Okay, so let's switch to the other side and see what we have. Okay, so I'm going to look at these points, the middle point between the different phases. Sorry, between the different T's. Okay, so the switch is now connected this way instead. So what happens now? Well, V1 we don't know anything about. In fact, we don't care because it's not connected to the system. Okay, V2 we do care about because we can now say that Q1 of NT plus tau is now going to be equal to C1 times V2 of NT plus tau. And V1 is just, not applicable more or less in this scenario. It's going to be applicable in other cases when we have more complex networks. All right, so Q1, and now we see something interesting because I have something saying something about Q1 at this point and Q1 at this point. And now I have V2 here and V1, so I have a sort of connection between the two different phases and the two different voltages. Okay, so how much or what happened here? Well, I transferred charge from the input to the output, so we're going to have to calculate the delta charge that we transfer. We're going to do one more little thing here, and that's to identify that the charge is preserved between these two cases. If I just, philosophically assume I have connected my switch like this for a short period of time, then there is no charge that can leave the capacitor. And then I connect like to the other side. So I do have some potential information about how much charge that's connected from input to output. Okay, so C1, and then we can define the delta charge. Like this, and I move the switch to the other side, and now I can notify or note down the charge on the capacitor at this phase as being C1 times the voltage V2 in this case for that particular phase, just when it touches the surface here. Okay, so then I can note Q1 of NT plus tau. So I'm adding a tau delay here. And then I get the voltage at that particular time point times the capacitor gives me the charge on the capacitor. And now, if we look at this, we have either a preservation of charge, or we have, something happening with the relationship between either the voltages, V1 and V2, in the equations here, and the charge on the capacitor Q1. So either maybe the charge changes, because there is a change in the voltage on the right-hand side of the equation, or the voltage changes such that there will be a change in charge on the capacitor. So there is some sort of interlink between the charge and the voltages here. The C1 obviously doesn't change, but the position of the switch changes and the network potentially changes during those two phases. All right, so let's look at the net transportation of charge from the input to the output. So I imagine that I have my capacitor like this, and then I have the possibility to switch this back and forth, and dependent on what's connected on the other sides, etc. But I don't care at the moment. I just say that, okay, I have a net charge going back and forth here. So I induce charge on the capacitor. I might move them out. I might move them back, etc. But at least I can argue that there is a net transportation of charge from V in to V2. Okay, and then I can define that net charge as dq, the difference at this time point. That's going to be whatever I had before, or what I have now, minus whatever I had before, NT. So something like this. And then I also know, I noted down here, the voltage times the capacitor. So I know that this is going to be equal to C times V1 of NT plus tau minus C times, sorry, V2 of V1 of NT, C1. Okay. And then, yeah, if I want to, I could pull out C1 here just for the sake of like this. Okay, and then I also know that from this discussion in the previous case, that the voltage is maintained on the output for the next half phase. So I know that V2 of NT plus tau is going to be V2 of NT plus 1, for example. So I could, if I want to, I could write this also at NT plus T minus V1 of NT. So I get a sort of 1 clock cycle delay here, 1 T. This is 1 T delay. Okay, so now what can we think about this? Well, I do have a transportation of charge during 1 T cycle. So I get a net transportation of charge during 1 T, and that's exactly the definition of a current. That's going to be delta Q divided by T. So difference in charge divided by the time it takes to do this, perform this operation. So we do have, if we want to combine this, then the I average of this clock cycle is going to be the delta C1 over T times V2 of NT plus T minus V1 of NT, like this. And now if we just compare this with a simple resistor, more or less, I equal to something times V. So if I move this guy to the other side, I will get V equals to something times I. Okay, so we do have something like a V2, V1, or whatever direction we want to use here. I get an I average and I have a resistor here. So if we compare with Ohm's law, we have I, obviously, V2 minus V1 equals to R times the I. And then we see that I average is simply going to be equal to, sorry, R equivalent is simply going to be T over C. 1 if you want then. So the equivalent resistance of this operation is something which is dependent on the time and the capacitor. And if you think about the logics here, if I have a small time, I mean very high frequency, this switch is standing and switching very fast. So during each period it's sort of switching, there is no, there's a small amount of charge being able to be transferred. If T is a large number, I have a long time to move the charge. And C1, the larger capacitance I have, the more charge I can bring into the plates for a certain voltage. So that would give me a lower resistance. So this is sort of logical in this sense. All right, so that's the basics of switch capacitance. So we could just make a small test circuit. So I'm going to launch, I'm going to expand this window and describe cadence a bit shortly. So I'm going to show you some SwitCap results here. But let's just do a first order analysis of a SwitCap circuit. Sorry, my pen is a bit odd. Okay. So, okay, so now assume I would like to make a small low pass filter. So I would like to do a resistor with a capacitor like this, R and C, and yeah, V out and V in. I would like to implement a low pass filter simply. So then I can replace this resistance with the switch capacitance. So I would do something like this. Oops, sorry, and a capacitor like this. So let's call it C2 just for the sake of having, and then I have a switch here going back and forth at the clock period like this. And I capture V out here, V in. So what do I get from this function? Well, I could just do a very simple assumption that V out divided by V in of S for the sake of mixing time domains here. Okay, so that's going to be, for this guy, it would be 1 over 1 plus S over 1 over RC, C2 in this case. Okay, and then I know something about the R here also, if I do implement it like a switched capacitor in this way. So this is going to be approximately equal to, and I replace the resistance here. So it's going to be 1 over 1 plus S divided by, and then R divided by C, so I'm going to get C1 divided by C2, and then I'm going to get T in the numerator. So I have like a sort of equivalent system. Let's just write that a little bit clearer. 1 plus ST divided by C1 divided by C2, something like that. So I'm going to get the ratio C1 divided by C2 and time. So that's one assumption of the transfer function. If I would just sort of do plug and play, plug and play, question mark. Will this work? We're going to see that this function is not fully correct. And we have to do some further analysis for that shortly. But we're going to make a slight investigation of C1 and C2 and a short discussion on when it's valid, etc. First, why is this attractive? Why? I mean, I have a ratio of C1 divided by C2, and that's quite easy to understand or get the point, realize. If I assume that C1 and C2 do have errors, and I want to implement some functionality here with a well-defined, I mean, this is the pole of the system, so I want the pole to be pretty stable and constant and not depend much on variations in C1 and C2. That's matching. So if I just look at the ratio here, C1 plus, and then I assume an error, delta C, and then C2 plus delta C2. So I assume they have some type of error. And then I can pull out C1 from the numerator and C2 accordingly. So C1 is 1 plus delta C1 divided by C1. C2, 1 plus delta C2 divided by C2. And then if I look at this, I assume this is my relative error. It's going to be equally large for both types of capacitors, regardless of size. So this is going to be an epsilon. That's going to be an epsilon. And then I can divide this or rewrite this division with the help of Taylor. 1 over 1 plus epsilon is going to be equal to approximately 1 minus epsilon. So this is going to be C1, C2, and 1 plus epsilon times 1 minus epsilon. And that's going to be C1, C2, 1 minus epsilon squared, like that. So we can quite quickly see that we get the square term of the error. And that implies now that we have a much smaller relative error if we have a ratio. So ratios less error than. Okay, T we don't care about. Well, we do care, but it has normally a very high accuracy. We have a well-defined crystal somewhere setting the T. So that's a well-defined parameter. And then we don't, we have compare apples and apples rather than apples and pears if we would have the R times the C here, because that would give you a term, an epsilon to the order of 1 rather than the epsilon to the order of 2. So we get a much more accurate system. This might be in, sub percentage, and now we get the square out of that. So a more well-defined system. We also have to make another quite important observation, 5. So we have to think in terms of what's happening. I do have, might have a continuous time input signal, but then I start sampling with the switches like this, for example. We will look at cadence shortly. And what does this imply, sampling? Well, I don't really destroy the signal. I just sample it in the time domain. So I don't discretize it with like an analog to digital converter would do. So I don't add any quantization noise. I just do something with a frequency spectrum. And what's happening is typically that I do get, due to the sampling and sample and hold operation, I get some sort of sync behavior like this. This is 1 fs, 1 over t. This is 2 fs, 3 fs. This is fs half. And obviously we need to comply with the sample theorem to begin with. So we definitely know that our sinusoid here, the frequency of that guy has to be less than fs half according to the sampling theorem. And further on we see that the sync, this is a sync function. So that's something like sine x divided by x. We see that it also distorts the signal close to fs half. We don't have a sort of equalized frequency range here. So I also should limit myself to a certain narrow band here where I can put my signal. So this is where I would like to be. So I do have a requirement that the sample frequency must be much larger than the signal frequency for switch cap circuits. At least this type of analysis that we do. We're going to look in next lecture how this can be relaxed and move ourselves closer to fs half here. We have here also let's leave that for now. Okay, so I'm just looking at the watch here, but I'm probably okay. So let's look at the more correct way of doing this. There are some assumptions here. This is correct to some degree, but we do get the wrong pole here due to this analysis, because what's happening here, if we look at the time period when we move the switch to the other side, then C1 and C2 are connected in parallel. So there is a certain charge sharing happening between C1 and C2 during that half period. That was not analyzed or used in this approach here. So we just assumed we could plug and play the resistor with a switch capacitor. And we will find that this method is not the right way of doing it. So we have to extend our analysis a bit. So what I would like to do is to probably do that first, and then I launch cadence, and then we will also come back to this guy. So we just have to do this step first, I think. Okay, so let's do a more correct analysis. So I do have a system which I can construct in this way. I do have my C1 and C2 like this, V out and V in during my phase phi1 and time period whatever. Okay, so what's happening here now is that we recharge C1 with our sort of ideal voltage source, which formulates or forms my input. And that means that the charge Q1 at NT is equal to C1 times V in of NT. We will soon throw out this T from the equations too. Okay, what else do we note? We can also note the charge on C2. So Q2 of NT at the same period is equal to C2 times V out of NT. So this is just some sort of observation that we do of our system in each phase. And it's obviously one equation per capacitor. Okay, and then once we're done with that, we can go to phi 2, the second phase. Now my net is so simple, so I will just toggle my switch that way and look at what's happening now. So first of all, I could actually write down the very same observation. So let's put a star on that. So I do my observations first. So Q1 now at NT plus tau. Well, that's connected to V out. So the charge on C1, if I indicate the plus here, just to have some sort of direction. So V out is going to be C1 times V out of NT plus tau. And then I also do the very same observation. NT plus tau is equal to C2 times V out of NT plus tau. So that's pure observations. So now we see that something happened here. I had V in here before on C1, and now I have V out instead. And then observation, and then we do charge preservation analysis. And what kind of preservation analysis can we do? Well, what happens with the total charge in the system between the two phases? So preservation from phi 1 to phi 2. Well, if we look at the system and assume that nothing is connected to V out, then all the charge that I had in phase phi 1 will be equal to the charge I have in phase 2. So that means that Q1 of NT plus Q2 of NT is equal to Q1 of NT plus tau plus Q2 of NT plus tau. So this is something called charge preservation. And here I now have a memory function. So I have the new charge equal to the old charge. So this is going to be the low pass filter, more or less, the element that remembers okay, so what else could we do? Yeah, well, we could normally do the next step in the charge analysis, and that's switching back to the original phase. So these are the typical general steps that we do. Phase 1, phase 2, phase 1, and then we note down the observations, and then we do charge preservation between both phase systems. So phi 1, okay, that's going to be the same equations. So I'm just going to type Q1, and now I type it this way, n plus 1 is equal to C1 times V in of n plus 1, and Q2 of n plus 1 is equal to C2 times V out of n plus 1. And what charge preservation do I have? So that's just my observations star. And preservation phi 2 to phi 1 when I switch back. Well, what's preserved? Nothing is preserved on C1 because I recharge C1 with my ideal voltage source. What I do preserve is the charge on C2 because that's now floating. If I move the switch this way, the charge on C2 is maintained. So from this one, I see that Q2 of n plus 1 or is equal to Q2 of nt plus tau. So I do see that this guy is going to be maintained also during the next cycle. All right, so let's compile all the equations we know, especially these charge preservation equations, and then we're done. So once again, we'll continue over the break here. Okay, so I'm going to have to capture this guy and this guy into the next page here. Okay, so I have, now I type them like C1 times V1 of n plus C2 V2 of n, so I replace the charge, is equal to Q1 of nt plus tau. So that's C1 of V2 of nt plus tau plus C2 of V2 of nt plus tau. Okay, so that was that preservation. And then what can this tell us? Well, that tells us that the charge is preserved on C2. Q2 is equal to the old one in the phase transition from pink to blue. And that also implies that the V out voltage must be maintained at the same level. Okay, so charge is preserved, C doesn't change, so obviously V out cannot change. So that implies that these two guys, V2, is now equal to V2 of nt plus 1t. And this also has to be equal to V2 of nt plus t. Or, if you like, V2 of n plus 1 and V2 of n plus 1. C2, C1 plus. And now I can see I can make quite nice difference equation out of this. So I have V2 and blah, blah, blah. So now we introduce the discrete time Laplace transform, i.e. the Z transform. So that gives us C1 times V1 of Z plus C2 of V2 of Z is equal to C1 plus C2 times V2 of Z times Z. I have a delay of 1 here, so I can multiply my Laplace transform or Z transform with a Z. And now I can move also V2 to the other side. So I get V2 of Z times Z, C1 plus C2 minus C2 equal C1 times V1 of Z. And then I can divide and get the transfer function. So this is now H of Z equal to V2 of Z divided by V1 of Z. And that's C1. And then I take divided by C2. And then I have a minus, and then I have 1 minus Z times C1 plus C2 divided by C2. That's my Z transfer function. All right. So observations. In each phase. And then you do charge preservations between the phases. And then I have to toggle from one side to the other and back. So that gives me 3 observations. And I have 2 transitions. So I need 2 charge preservation equations. So we have this guy and that guy. 1, 2, 3, plus these two transitions. And then it's simply about identifying the different, equations or knowledge I get from these operations. And I get the relationship between something at one clock cycle and something at another clock cycle. And then I use my Z transform. And blah, blah, blah. This is just pure algebra, more or less. And I get an expression. So how does this comply? I mean, this is now in the discrete time domain. So how does that align with our continuous time domain? Well, we can go and have a look at that. So the relationship between discrete time and continuous time is given by some sort of mapping. It's not super obvious, perhaps, but we do have, in discrete time world, we have a unit circle like this. And in the continuous time, we have a imaginary plane like this, where we care about the y-axis, the imaginary axis, and in the discrete time world, we care about the unit circle. And this unit circle is mapped on this imaginary axis. The boundary, this unit boundary is mapped on this axis when we compare continuous and discrete time domains in the frequency domain. But remember, we did require that the sample frequency has to be much, much higher than the signal frequency in order to avoid this distortion due to the sink of the sample and hold, which means that we already know that we have a quite narrow gap of frequency here compared to the signal, which means that if I look at my unit circle, I'm sort of only operating in a quite narrow angle here, like this. This is my frequency of interest, and that maps then, this is approximately pretty linear, this short region of the unit circle, and that's then mapped to a certain region on our continuous time domain. We know, for example, if we take the boundary between Laplace and Fourier, this is going to be equal to Z is going to be equal to e to the st on the unit circle. And if st is a small number, which it is for this small wedge here, then we know, according to Taylor, that's going to be approximately equal to 1 plus st. And this is now my mapping from the discrete time to the continuous time domain. I have my st term here. If I would have a larger span, I would have to do mapping with also squared and cube terms, according to Taylor, but now we say they are ordo st. So I do have a mapping with a sample frequency and a continuous time variable connecting to the discrete time variable through this sort of operation. Sorry, -1 should be here. That's going to be approximate this. That should be more correct, sorry. So that's the mapping. Okay, and that implies that I can take my equation, and I have minus C1 divided by C2, 1 minus Z now becomes ST, and then I have a C1 plus C2 divided by, sorry, I have C2 divided by C1 plus C2, like this. Now I can compare this with my formula that I calculated with a plug and play method. Where did you go, Mr. Plug and Play? There we are. Okay. So the plug and play method, where I just assumed I could replace my resistor with a capacitor, that gave me some assumption here which was incorrect. We get C1 over C2 and didn't cater for the charge sharing between these two. during this phase. And we see now if we import and compare the formulas, there should be a term C2 divided by C1 plus C2 here instead, compared to that expression. So something was a bit dodgy there. All right, so comparing the two domains gives us something which, you know, have a slight shift of the capacitance there. Okay, I'm going to fix this a little bit later because there is a slight error with the sign here. So I'm going to mark this here and fix that in the video later. Oops. All right, so let's just switch to cadence and have a little bit of simulation going on. And then after this, we're going to connect the capacitors to operational amplifiers instead and work from there. Okay, so let's expand this window and then just a short demo. And right, so cadence. So in the lab, for this course, I have created some help circuits. So there is one generator that creates non-overlapping clock phases that will be helpful for you when you switch or control the switches. So we will get two clock phases, one on and one off. And they can't be overlapping because then I will turn on the switches at the same time and charge will be shared and I will destroy the operation. So I really have to distinctly move my switch sort of up and be in the position between the two states for a short period of time, just to avoid any shorts. Right, and I also create this switch, a three-way switch in this particular case. So that's going to be my switch that either, you know, turns to the left or turns to the right. So I either connect the V in or I connect the V out. And then we simply simulate this circuit with transient analysis. There are other ways you can simulate with spectra RF, where you can do frequency analysis of this switching operation. You will do that in lab 3. In lab 2, we will mainly do transient simulations. So I've created some test cases here and I press run then, and I get this curve. Okay, so I can see in this particular case, I have not connected anything else to the output node. And I plot my input voltage and my output voltage. And here you can see that operation that I was talking about, that during one of the phases, the output voltage will hold constant. And during the other phase, it will simply track the input and charge the capacitor. And just at NT, I will start releasing the switch at that particular and sample that voltage and hold it, etc., etc. So I do have some sort of staircase operation going on, and it's probably also important to realize that we track the input or the voltages during half the clock cycle and I hold the other half cycle. So the operation is a little bit dodgy. It's a little bit of discrete time and then continuous time to some extent. Okay, so we can also look at the current. I plotted the input current. It's not super interesting perhaps, but charging a cap with very low resistance is more or less instantaneous. If I assume that the switch has a very low on resistance, it will then charge with a very, very high frequency. So in the labs, you will test what happens if the switch resistance is much higher. So you get the sort of delay for the signal to go from input to output. Nevertheless, I do have some sort of net current. It's not obvious from these curves, and also the simulator struggles a bit, but there is a net charge jumping onto the capacitor. And then I sort of could derive by integrating and divided with this time that we did in the beginning of the lecture. But let's ignore that for now. Okay, so this is just a simple sample and hold operation. And now we could also look at what happens if I connect my capacitance to the output. So now we have the case that we just investigated. So I have a switch capacitor acting like a resistor, and then I have an additional load capacitance at the output. So I would assume some sort of low frequency behavior here, or filtering at least. So let's save and run this simulation and take a look at the curve. Did I get into, there we are, simulate. Okay. Right, so here we see the effect. So now we notice that my original signal, the yellow one, which might be hard on the video, but at least my yellow one is my original input signal. And then I had a case where I have a phase shift, as I would expect in a low pass filter. So I would not only would I attenuate the signal, I would also phase shift it, which we can quite clearly see here. The number of degrees, one could argue, but maybe 20 degrees or something phase shift here. Yeah, we simply see also that there is an attenuation of the amplitude. And now I could increase the sample frequency 4 times, for example. Let's see what happens. So I would expect to get lower resistance because I decrease my resistance. We had R equal to T divided by C, so that's 1 over F times C. And now I increased F, I reduced R, I moved the pole to higher frequencies, and that's what we see here also now. The low frequency input passes through the system much more conveniently here. And we only have a small phase delay from the filter. And then we could, for the sake of discussion, then we could also decrease the capacitance. That would then increase the resistance with that argument, T over C. So let's put a femtofarad here. Maybe that's a bit aggressive, 10 femto. And run the simulation. And now I press. Okay, so now I did the resistance 100 times higher. And now you see we attenuate the signal quite dramatically. And yeah, the phase shift is almost 90 degrees here. So we probably, you see you have a minimum here and a maximum by the zero transition here. So we're almost down at cosine. So we're almost 90 degrees phase shift. So we have rolled off all the way beyond the pole. So we see quite clearly how it works. I mean, we have an RC happening. We can set the amplitude or the sort of pole position with the sample frequency, and also changing the size of the capacitor. So it seems to behave the way it should. All right. Okay, so due to the misdemeanor about the time and Zoom links, I'm going to continue directly here to be able to stop at 5. And I guess you can grab a coffee while you're listening to me or something. So what we will do now is to start adding active circuitry. Why do we need to add active circuitry? Well, if we look at cadence here, we see that this is quite sensitive. If I would connect a additional drive circuit, circuit on the output of this RC link, and that would be having capacitance, that would influence the transfer function, because that would sort of sum up together with this capacitor here. So I would like to, and it has sort of zero driving capability. If I need this output voltage to drive something else, I can't do that with a pure charge on the cap. So I have to connect my operational amplifier or some sort of buffer or something that sort of isolates this output voltage. So that's the plan for the rest of the lecture. So let's get rid of cadence and see if we can do some simulations towards the end of the lecture. So the plan is that now I will instead connect it like this. I will simply use, this guy as a template. And now actually we can do the plug and play approach. Why can we do that? Well, that's because we have here our virtual ground of the op amp, which means that voltage is constant 0, and it doesn't load. Well, of course it loads due to the perhaps internal components of the op amp. It could load the capacitance, but at least that load is sort of constant. So let's just look at the following. So I connect the capacitor like this, and then I connect up here like that, and then I connect V2 here and V1 here. And then we have C2 here and C1 here, and the switch operating back and forth. Okay, and now it's quite good to indicate a direction, or at least a reference direction of my capacitors. It doesn't matter where you put the reference, as long as you let them be there for the rest of your analysis. So I'm going to assume that my positive end of the capacitor here is pointing upwards and towards the output here. Why do I do that? Well, that's because we have switches now. So assume I could actually add a switch on the other side of the cap, and then, hypothetically, I could more or less connect the capacitor wherever I want into the network. I could have two cables connecting, more or less anywhere. And that's important to keep the direction in order when we do our charge preservation analysis, because then suddenly we could have a minus coming into the equation because we're sort of flipping the capacitor. All right, so let's, so yes, this plug and play assumption that will give us, plug and play would give us the assumption that V2 divided by V1 would be simply, the standard minus 1 over SRC2 equation that we know from op amp analysis. 1 over, so that's going to, if we do the, we'll get minus C1, C2, and then ST. So that's my integration operator, and that's my gain, more or less. So we can also here observe that the gain is dependent on T. And that's not really a surprise, because that's actually what we just determined also in cadence. The faster we sample, the more charge we accumulate on C2, the more gain we get. So that's important also for lab 3, then lab 2 and 3 to understand. All right, so we're going to do an analysis of this one, and then we're going to, once we've done that, we're going to make a small analysis and suggest an improvement to that one. All right, so let's do the analysis that we did before, but on this particular circuit, and then we'll do it yet one more time today. So we have two phases, phi 1 and phi 2, either connected like that or connected like that in the other direction. So we have to do our 3 steps, observation in 3 steps and preservation or transportation in 2 steps. So let's start with phi 1 then, and just observe the charges on the different caps. So Q1 at N, That's simply going to be C1 times V1 of N. So I connect my V into the output, sorry, to the capacitor, positive plate of the capacitor. What about Q2? Well, that's going to be the charge on C2. I know that's virtual ground due to the op-amp operation, so that's going to be 0 volts. So I know now that Q2 of N is equal to C2 of V2 of N. All right, what do we know in the second phase? Q1 of N plus a half. That's going to be C1 times, but now the switch is connected like this to virtual ground and normal ground. So that's going to be 0. Q2 of N plus a half, that's simply going to be C2 times V2 of N plus a half. That hasn't changed at all. Well, it has changed. Potentially the voltage has changed, but the expression here, it's always connected to virtual ground and output, so that shouldn't be any surprise there. Okay, and then we need to go back to phi 1, and then we do the same observation, and nothing strange here really. We just observe that Q of N plus 1 is equal to C1 of V1 of N plus 1, and Q2 of N plus 1 is equal to C2 of V2 of N plus 1. So obviously sort of same like the observation we did before, but we're going to add the preservation things happening between these two equations or states, and then we can sort of fill in the gaps. Okay. So let's investigate the first preservation. Okay, so we go from this scenario, we have the switch pointing upwards for a short period of time and then switches here. So what's happening in this particular case? Well, this C1 will now be shorted between ground and virtual ground, so it has to drain all this charge. But the charge is not lost in vain. Instead, it has to go up here and put itself on the negative plate of C2. And this charge is just flushed through the ground. So I do have an accumulation happening here. I have V1 charging C1, and then I flush it and move the charge up to C2. So I can say that Q2 of N plus a half minus, because I have the negative side of the charge here, plus, equal to, minus the charge that used to be there before. So I have Q2 of N plus all the charge that came from Q1 of N. So I have the new charge and the old, and then extra. So that's my preservation. And I can notify here that Q1 of N plus half was equal to 0, just for the sake of observation. And here we see the accumulation starting to happen. Okay, so that's the first star. What about the second? How cross we had? The second one from phase phi 2 to phi 1. So in this particular scenario, I have my switch pointing upwards for a short period of time, and then I switch it to V1. So V1 is going to recharge C1 with an ideal voltage source. So there's no preservation happening here, it's just recharged. C2, however, will keep its charge on that plate. For C2, I could argue then that Q2 of N plus 1 is equal to Q2 of N plus 1/2. One could argue that it's the negative plates that's conserved, but it doesn't matter in this case. It'll be the same on both sides. All right, so yeah, since that's preserved, we can quite easily just connect these two equations directly and just fill in the blanks. So we have minus C2 times V2 of n plus 1 is equal to this guy, which is here, minus Q2 of V. So that's C2 times V2 of n plus that's going to be V1 of n times C1. All right. Yeah, so that's more or less the difference equation already served for you. However, let's go to the Z transform. So we get minus C2 V2 of Z times Z is equal to minus C2 V2 of Z plus V1 of Z times C1. And obviously we can connect the stuff together. We get V2 of Z divided by V1 of Z equal to H of Z equal to, yeah, minus C1 divided by C2. And we also see here that C2 is both multiplying V2, so we're just going to have Z minus 1 in the numerator here. Denominator, sorry. So that's my transfer function. And if one looks at this expression and recaptures some from preschool, one will know this is a discrete time accumulator then. Accumulator, or like we say in continuous time world, it's an integrator. And we know it's an integrator because that's exactly what we mimicked. That's an integrator. We have 1 over S something. So continuous time world, it's an integration. In the digital world, or discrete time world, I should say, this is an accumulator, the Z minus 1 functionality in the Laplace transform. And doing this scaling here also, we can quite easily verify that too. We have this expression. So H of Z is equal to minus C1 divided by C2, Z minus 1. And the transfer Z is equal to E to the EST, which is approximately 1 plus ST. So Z minus 1 is going to be ST. And that's then in the discontinuous time approximately equal to that. So we see that the plug and play works in this case. In this case, we should mention. And that's mainly because we didn't have any charge sharing on the capacitor. Okay, so it's quite easy, to be honest, to take the analog template, do something that would be something, you know, like plug and play, but we probably have to do some more tricks later down the road, but more or less trying plug and play. If we can observe that there is no charge, you know, there is no C2 connecting here to my C1 and destroying that transfer function, then we can do a quite simple plug and play like this and land at the same type of transfer function with a discrete time implementation. So no resistor and quite easy mapping from an analog template to a discrete time template, or discrete time implementation, I should say. We will have to modify this circuit a bit because it is sensitive to some extent. It's sensitive in the sense that once you want to implement this circuit, it's going to be sensitive towards additional capacitance. Sorry. Associated, for example, with switches and op-amp inputs, and a lot of parasitics happening between the different places here. Because what's going to happen here, I'm going to charge, especially this parasitic capacitance, which is associated with a plate here. I'm going to charge that, and then during the next phase, I'm going to move the charge which was stored on these parasitic capacitances to the output. So even though I think I implement the C1, I will get this additional, well, garbage more or less, that will influence my transfer function. So there are ways to create a parasitic insensitive circuit. So this is a parasitic sensitive circuit because it has potential capacitors here that influence my transfer function. So we're just going to wrap up the lecture by looking into parasitic insensitive accumulators. Right, and I'm going to draw that. So it's going to look like this. So I have my capacitor and like this, and I put my V in here, and I put my ground here. I take my other ground or same ground to a operational amplifier positive input, and I connect minus plus, C2 here and C1 here. And then I introduce an additional switch here. Okay, so why is this parasitic insensitive? Well, assume I have a capacitance with this node or up here to this node. So that's might be difficult on the video here, but I do have a capacitor here connecting to this side of the plate. And if we look at the first phase, when the switch is connected down here to this output, this plate will be connected between ground and ground. So it's not going to be charged to anything. And during the next phase, it's going to be connected to ground and virtual ground. So 0 and 0 volts. So during the next phase, it's going to be also 0. So nothing is happening with this charge of this node. This capacitor on this side of that plate will be connected to V in during one of the phases and to ground in the other phase. So either I will charge with my ideal voltage source a certain net charge, and then that net charge will just be flushed down to ground during the next phase. And that doesn't influence my transfer function. It just influences some additional load on V in, but it doesn't influence the accumulation here, which this capacitor did, because then that capacitor would happen or end up in parallel with C1, so I would get a transfer function which would be something like C2 divided by C1 plus the delta C. All right, so it's quite important to use parasitic insensitive accumulators instead then, because you get a much more accurate transfer function. So for the sake of training, we will run through the analysis here again. You have to demonstrate that also in your lab reports. and yeah, present that for lab 2 then, some sort of analysis. Okay, so once again, we have to investigate. We have two phases, we have two capacitors, so it's not much to write in this particular case, but phi 1, as it's drawn here, for example. Notice that we could flip one of the switches here. That will actually change the transfer function. We will see that shortly. But what happens is that we get a delay of the input signal by 180 degrees. So I can choose my delay of my circuit by setting these switches in different starting conditions. I could also sort of move this and have that as a starting position. And that would also give me 180 degrees phase shift. So it's quite intelligent block in that sense, in its simplicity. Okay, so phi 1, we're going to charge C1. So Q1 of N is going to be C1 times V in of N minus either 0 or virtual ground. In this particular case, virtual grounds is going to be minus 0. And then Q2 of N is going to be C2 of V2 or V out, VO, I call it, minus 0. Phi 2, we have now switched the switches to this case and that case. Now the capacitor C1 is connected between ground and ground, so we're going to flush C1. So Q1 of N plus a half is 0. Q2 of N plus a half. This switch is pointing here. Nothing has changed for C2. That's C2 of VO N plus a half. And then phi 1, again, the third case, perhaps stating only the obvious. Q1 of N plus 1 is equal to C1 times V in of N plus 1. And Q2 of N plus 1 is equal to C2 times VO of N plus 1. Just replicating those. And then we look at the transitions from phi 1 to phi 2, phi 1 to phi 2. What's happening there? Well, we already stated we're sort of flushing charge here. Yeah, as it looks now, we're sort of losing all the charge we had, to be honest. So nothing is preserved on C1, but we have preservation on C2. So we know that then Q2 of N plus a half is equal to Q2 of N. And then we go phi 2 to phi 1. So stepping back or going to this blue switching position. What is preserved then? Well, we recharge the plate on this side from V in, but if you look at it, the charge on this side here is preserved. So whatever is stored on this sort of network here is going to be preserved. So essentially this V in, even though it looks like it's charges with C1 during this blue phase, is sort of going to steal charge from C2. Now one can argue what's positive and negative, of course, but sort of philosophically stealing charge from C2 and use that to set the charge on C1. So the charge in this cloud will be maintained. So we have that Q2 of N plus a half. And now I type minus there because I want to use my plates. We didn't indicate any plus, but let's do plus here. So minus side charge Q2 is from the previous phase plus the previous charge on C1, but that was 0, so we don't have to care about that. That's going to be equal to the negative charge of Q2 of n plus 1 plus the negative charge of Q1 of n plus 1. So we preserve, and then with the help of these direction markers, it's quite easy actually to you know, not lose any minuses or anything on the equations here. And we see that we can use this guy inside here to get the quite neat transfer function. So we can immediately combine these two guys. Q2 of n minus is equal to minus Q2 of n plus 1 plus minus directly Q1 of n plus 1. And then we have these three, and we have these three equations that helps us to identify voltages and capacitors and put them into this equation. So let's wrap that up. We get let's borrow this like this. Okay, so we get minus C2 times V2 of n, and then that's equal to minus C2 of V2 of n plus 1 minus C1 of V1 n plus 1. And now I use the 2 here, even though it's V2 is V out and V1 is V in. Right, and then we're actually down to the same function we used to have. So if I just more or less directly can go to the Z transform, we see that this is equal to, yeah, let's do the steps here for the sake of the, so minus C2 V2 of Z is equal to minus C2 V2 of Z times Z minus C1 of V1 of Z times Z. So there's a additional Z here, but combine them. So minus C2 V2 of Z 1 plus Z is equal to minus C1 of V1 of Z times Z. And yeah, V2 of Z equal divided by Z is equal to H of Z equal to minus C1 times divided by C2 times Z divided by 1 plus Z, and then minus minus becomes plus here. And now I just have to find a minus to correct myself. Let's see, what did we miss? We want to preserve the charge. Yeah, so I have to fix this at some point. There should be a minus here. Like this. So somewhere here I lost a minus in the middle of everything. So I have to correct that. Let's not, well, let's spend a second on that. All right, so that's the transfer function, and that's the correction. Moving minus to the other side gives me a plus. Okay, so anyway, so here we have a transfer function which is an accumulator also. If we go back to the one that we calculated before with the plug and play method, this guy has also Z minus 1, minus, but here we had an additional Z in the transfer function. That's a delay, more or less. So that's just a delay. And the delay comes from the fact that dependent on how we connect the switches here, it depends on when we actually get the input signal to the output. And the thing was here that we sort of steal charge from the capacitor of C2, so it sort of relates to the charge that was already on C2. So there's a certain delay in the transfer function from input to output. Okay, there is a trick we can do. We can change the location of the switches, flip one of them, and then this Z would go away. So there's also a certain accumulator type which has 180 degrees phase shift or not. So depends on the switching. So with switch positions, you can control delay. Plus minus, 180 degrees or 0 degrees, or say 360 degrees for that sake. I delay 1/2 or 1 complete clock cycle. So that's quite handy. If you're going to use this in a loop where you need negative feedback, you can just flip the switches one phase, and then you actually more or less invert the signal in the sense of signal processing sense of view. All right. We have a lab on Tuesday